April NASA Night Sky Network member webinar. We're hosting tonight's webinar as usual from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome our guest speaker, Dr. David Williams from Arizona State University. But before we introduce David, here's Kat with just a couple of announcements.
Hello, everyone. So the first thing I want to point out is this lovely Psyche art behind me. And this was painted by Peggy, who is with the Broken Arrow Astronomical Sidewalk Astronomers, excuse me, Broken Arrow Sidewalk Astronomers. So I do want to shout out Peggy for sending me this art because it's beautiful. With that said, if anybody has any space art that they tend to create, feel free to send it to us at Night Sky Network. We love looking at some of your more creative ideas. You can send it to us at nightskyinfo@astrosociety.org. Now, getting into the news, in the coming weeks, we will have more details about the solar toolkit that Brian and Vivian have been working on for the last few months. If your club is active, you'll get this toolkit sent to you automatically, so you don't have anything that you need to do. We do ask that you check your shipping address just to make sure that it's up to date, but as soon as it's back from the printers, it'll be sent to you with no delay. Now, if you are a club and you are listed as an associate club on our website, it means that you are part of the Night Sky Network, but you're not an active member. So what I absolutely recommend is to review the link that I've posted here in the chat on how to become active on Night Sky Network. For those of you listening on YouTube, Night Sky Network is a coalition of 400 astronomy clubs across the US. And if you're not connected with your local astronomy club, you can visit our website and find the one that's closest to you. And for all of our clubs that are joining us tonight, your reporting of your events helps keep us going. So we thank you so much. And I'm going to turn back over to Brian.
Great. Thanks, Kat. So for those of you on Zoom, please remember that you can find the chat window and the Q&A window in your Zoom taskbar. Please feel free to greet each other in the chat. Also, you can let us know if you're having any technical difficulties in the chat, or you can send us an email at nightskyinfo@astrosociety.org. If you have a question you'd like David Williams to answer this evening, please type it into the Q&A window. That will really help us keep track and know if we've answered your questions or not. And Kat, if you could hit the record button, that would be great. Okay, again, welcome to the April NASA Night Sky Network webinar. Dr. David Williams is a research professor in the School of Earth and Space Exploration at Arizona State University in Tempe, Arizona. Dr. Williams is the director of the Ronald Greeley Center for Planetary Studies, a NASA-sponsored planetary data center at ASU. David is currently performing research in volcanology and planetary geology with a focus on planetary mapping, geochemical and remote sensing studies. He's been involved in a whole bunch of different missions over the years, and you can read his little bit longer bio on the Night Sky Network website. Currently, he's the co-investigator and the deputy lead for the multispectral imager on NASA's Psyche mission, which he's going to talk about this evening, which launched in October 2023. He's also a member on a couple of other current missions, the Italian Janus camera team of the ESA Jupiter Icy Moons Explorer mission. And also recently, he was elected a fellow of the Geological Society of America. And because he's done so much work with asteroids and done other really great stuff, he's had an asteroid named after him. And so it looks like it's 10,461 Da Williams. And he's also he's a former secretary of the Planetary Sciences section of the American Geophysical Union. Please welcome Dr. David Williams.
Hello, everybody. It's a pleasure to be back and talking to you here on the Night Sky Network. And because I did speak to you guys once before, I think it was during the COVID-19 pandemic. So here is just a picture of two planetesimals colliding, and what their consequences of that might be is what we think the Psyche asteroid is about. And so that's what I'm going to talk to you about today, is the Psyche exploration of a metal world. And I saw already, before we started here, a question. I don't understand the connection with Psyche and metal. Well, hopefully I will explain that to you during the course of my presentation. So before I begin, let's just sort of set the stage about the exploration of space and why we choose to explore space. There's a variety of reasons we do that. As a scientist, I want to do it to understand the universe, understand the cosmos, how it formed and how it's evolving. But there's a bunch of other reasons why we choose to explore space. Nations do that because of national prestige. They do it for national security, maintain the high ground, protection from adversaries. We do it for economic reasons, to identify and exploit space resources to build national economies. We do it for sustainability, to better preserve the Earth and its citizens. We do it for education and inspiration. We want to inspire and create the next generation of scientists and engineers, which is increasingly important in our technically dominated society. And then finally, we do it for survivability, because the reason why the dinosaurs aren't here is because they didn't have a space program. They couldn't detect and deflect that asteroid that wiped them out 65 million years ago. And so that we avoid that fate, we need to transform humanity into a multi-planet species. So that leads us to NASA. When people think about NASA, they think about, I don't know, the Apollo program or the space station or the astronauts. And that's just one very small part of what NASA represents. NASA's actually split up into 5 mission directorates. Aeronautics research does, as it sounds, research on how to move people and cargo around the Earth. Space technology, to develop the technology to better explore space. The human part of NASA is in 2 separate parts. The Space Operations Mission Directorate does all the stuff in low Earth orbit. So the commercial capsules and the International Space Station, that all falls under that. The Exploration Systems Development Mission Directorate is the one that's involved with deep space exploration. So the Artemis program to return humans to the moon and then moon onto Mars part of the program, that's all under that directorate. And then finally, we get the Science Mission Directorate. And that's the part that funds all of the scientists who do research on the different parts of the universe here. And the Science Mission Directorate is split into 5 divisions. Heliophysics studies the sun, Earth science studies the Earth, planetary science studies everything in our solar system except for the sun and the Earth, astrophysics studies everything outside the solar system. And then the 5th one is a very cross-cutting division that focuses on biological and physical sciences research wherever it occurs in the Science Mission Directorate. So with that background, let's now talk about how we choose to explore the solar system. And, it may seem like it's a haphazard approach because you hear about rovers at one place and flybys at another and orbiters, but actually it's a very well thought out phased approach. We do what's technically possible, what we have the engineering skills to do and build. We do what's affordable, what Congress will give us the money to do. We do the easy missions first, accomplish them successfully, and then move on to the more complex missions. And you see in this list here the order in which we accomplish that. So the least expensive, the easiest to do is a planetary flyby. You fly by a planetary object, you take pictures, collect data, transmit it back. That gives you the initial reconnaissance of the object. Next, you want to go into orbit. So you design an orbiter mission, and that gives you a global data set as the planet rotates as you orbit around it. When you know about an object from orbit, of course, you want to land. And there's different ways you can land. You have hard landers that descend, and they take pictures as you descend, and then they smack into the ground. The instruments are all broken. So we tend not to use those if we can use a soft lander, which has parachutes, retro rockets, airbags, something to slow it down so it lands and all the instruments work, and you get those wonderful 360-degree panoramas and really see what a surface looks like and can take measurements. But as often happens, you see something on the horizon and you want to go over there and see what else is out there. So that's where you need mobility, and that's where rovers come in. So that's mobility on the land with walkers or wheels, or if it has an atmosphere, it may be balloons or helicopters, drones, just like Ingenuity that we saw on Mars in recent years. The next most expensive and hard to do is sample return, where you collect a sample of rock or soil, dust or ice or atmosphere, put into a container, blast it off, and bring it back to Earth, where we can study it with all those wonderful machines in our laboratories that tell you all the great information about it. That's easy to do for low gravity bodies like comets and asteroids, but much harder to do for bigger objects. And then the final one on the list here are the crewed missions to send humans to orbit and land on planetary bodies. So this chart shows you the status of solar system exploration here in 2025. And if you can see on there, you see those different modes of exploration across the top, the objects of the solar system from Mercury all the way out to Pluto and the Kuiper Belt. You see the telescopic observation is all filled in because that's how everything was discovered. You see the flyby column is now filled in, starting with the Mariner 2 flyby of Venus in 1962 and concluding with the New Horizons flyby of Pluto in 2015 and even a Kuiper Belt object in 2019. We've completed the initial reconnaissance of the solar system. As you move further to the right, you see that mostly the inner solar system has been explored with orbiters and landers. The outer solar system, we haven't reached, the ice giants, Uranus and Neptune yet. Rovers, we mostly have just had those on the inner planets. Oh, by the way, the colors on here, white are past missions, green and blue are missions that are in flight or functioning. Things that are in yellow have been proposed but not funded. And you see MSR, the Mars Sample Return, is lit up there in sort of red, that it's under development. And whether it'll be funded, we don't know yet. And then the final column for crewed missions, we just have had astronauts on the moon with Apollo. So what I like to say is our goal is to completely explore the solar system with robotic spacecraft first, and then humans. And once that's done, then we'll be able to boldly go where no one has gone before, as they say in my favorite TV show. So that's all preamble here. What I'd like to talk about now is the NASA Psyche mission. So let's review a little bit about asteroids, what they are, where they're located, and why we care about an asteroid named Psyche. And then I'll talk about the Psyche mission itself, its objectives, its instruments, its operations, how things have been going since we launched, what we hope to learn and expect when we get there, and then a quick look at what's happening with some of our other planetary asteroid missions, and then go into Q&A. So you guys are all amateur astronomers, so you probably know all this. Asteroids are minor planets, protoplanets. They're the rocky remnants left over from the formation of the solar system, like 21 Lutetia that you see here, mostly composed of silicate rock, dust, and maybe volatiles. In this case, volatiles means ices of some sort, probably water ice. Most asteroids are located in the main belt between the orbits of the planets Mars and Jupiter, but there's also interesting populations of asteroids in other locations, including the Lagrange points of Jupiter's orbit about the Sun. Those are the Trojan asteroids to be visited by the Lucy mission, our sister mission. The Centaurs between the orbits of Jupiter and Neptune. And then, of course, there's the near-Earth asteroids, the ones whose orbit come to or cross that of the Earth. These are the potentially dangerous ones. And, NASA has a whole planetary defense and near-Earth objects program to try and detect, discover, map out the orbits, and deal with those asteroids. And then the animation at the bottom, of course, is the occasional extrasolar asteroid from Oumuamua from a few years ago that passed through our solar system. So we're talking here about asteroid number 16 in order of discovery, Psyche, and that's a main belt asteroid. I should say most of what we know about asteroids are from reflected light telescopic spectra. You guys all know this because you work with telescopes. They've been classified in various types. Carbon rich are most of them, stony, silicate rock. The Trojans are the dark and primitive DNP types. Asteroid number 4, Vesta, is V type because it's made of volcanic minerals. It was probably volcanically active early in its history. And then there's the M type. And in this case, M stands for metallic. We think that this is dominated by iron and nickel metal, and there's a whole bunch of iron meteorites on the surface of the Earth. And the M types may be exposed cores, iron nickel cores of asteroid parent bodies. So between comparing the telescopic spectra and the spectra of meteorites in laboratories, because most meteorites come from asteroids, the conclusion at present is asteroids are the rocks that never coalesced into a planet. The gravity of Jupiter out there disrupted the main belt and kept a planet from forming in that location. So here's just a quick chart of asteroid exploration. You'll notice that most of the entries on this are not bold text. The ones that are in bold are missions that were dedicated for the exploration of one or more asteroids. Everything else, asteroids sort of got short shrift. They were ride-alongs or something that you observed in a flyby on your way to the main target. And I was there as a grad student when we got our first images of 951 Gaspar and 243 Ida during the Galileo going through the solar system before it got to Jupiter. You had to wait till the near mission at the start of this century. They actually have a dedicated orbiter of 433 Eros. The sample returns from the Hayabusa missions, the Dawn mission to study the two most massive asteroids in the main belt, Vesta and Ceres. And then most recently, OSIRIS-REx, which returned the samples of near-Earth asteroid Bennu and the wonderful results that we heard about that earlier this year. And then in green are the two active asteroid missions, Lucy and Psyche. So here's one of my favorite graphics. Emily Lakdawala of the Planetary Society made this before the Dawn arrival at Vesta in 2011, showing a smorgasbord of asteroids and comets and how they appear as irregularly shaped, rocky objects, lots of impact craters. You might see boulders, you might see lineaments there, but these remnants from the formation of the solar system. So in terms of size, here's Mars, Mercury, the Earth's moon, and dwarf planet Ceres and asteroid Vesta, all the same size scale. So, compared to planets, asteroids are much smaller. But a good question one might ask is, how small can an asteroid be and still have planetary processes like differentiation in the crust, mantle, and core, volcanism, and other things happening on it? That's something that is very much being studied now. So let me talk a little bit about asteroid Psyche. Psyche was the 16th asteroid discovered. It is the largest M-type or metallic asteroid in the solar system with those dimensions you see there, discovered by the Italian astronomer Annibale de Gasparis of Naples back in 1852. Asteroid 16 Psyche orbits about 2.9 AU toward the outer edge of the main belt. It takes about 5 years to orbit the sun once. It rotates relatively quickly in about 4 hours. And you can see in these telescopic shape models, it's not round, it's more potato shaped, and probably from being hit quite a bit. So, it is the largest M-type asteroid. It could be the source of one or more families of iron meteorites. It's denser than all the silicates. Probably, though, it does have some porosity, which implies a regolith of some sort on the surface. Maybe there's carbonaceous gunk deposited. Maybe there's water ice deposited. So that's one of the reasons why we want to go, is to discover what its nature looks like up close, because an M-type asteroid hasn't been explored before. And of course, all sorts of comparisons to the different iron meteorite families are being done right now. Could it be the homeworld of pallasites? Could it be the homeworld of another type of iron meteorite? Those are questions that we hope to answer from the mission. So here you see asteroid Vesta, which is basically the size of the state of Arizona or New Mexico if you just laid it down on the surface there, compared to a lot of the other asteroids that have been visited. You see 21 Lutetia, which was the big one in the prior graphic. So how does Psyche compare to this? Well, Psyche is in between the two. So Psyche is basically the size of the state of Massachusetts, if you leave off Cape Cod, or the distance between Phoenix and Flagstaff, if you've ever made that drive on the I-17. So when you develop a planetary mission for any object, the first thing you need to do is come up with a science goal, a driving question, and a series of science objectives, because those will lead you to what kind of observations, what kind of measurements, what kind of instruments, and what kind of a mission architecture you need to accomplish that. And so for in the Psyche mission, our overriding question is 16 Psyche the core of an asteroid parent body? And to answer that question, we have specific science objectives. Is Psyche actually a planetary core, or is it a piece of unmelted metal left over from the formation of the solar system? What are the relative ages of its surface? Do small metal bodies incorporate light elements expected to be in a high pressure core like the Earth's core? Does Psyche form under more oxidizing or reducing conditions? And what is the topography of this world? We already know it's potato shaped and has indentations that look like craters. Is there more to it than that? So the idea that we had was, the formation of the solar system, the gas and dust cloud that formed after the sun formed. The stuff is going around the sun. It starts to impact each other. So you've got pebbles forming cobbles, forming boulders that form planetesimals that will impact to form planetary embryos that then coalesce down into the 8 inner planets that we had there. But in some cases, you might have impacts that don't accrete, but rather blow material off. And that's one idea we had about Psyche. So you imagine a liquid metal core with a silicate crust and mantle that's hit by what we would call a hit and run impact that knocks most of the silicate crust and mantle off. So you have this spinning molten metal that is pulled together by gravity. It's going to crystallize the metal from perhaps the top down, could even from the inside out. It could develop a magnetic field that's preserved. You're going to expel sulfur because sulfur and metal are immiscible. They want to separate. Eventually, you'll freeze together. You're going to be impacted. So these cartoons on this slide is one possible route to explain what the nature of Psyche, asteroid Psyche is. So once we know our objectives and we know what measurements we need to make, we need to build a spacecraft. So here you see the spacecraft looking a lot like an Earth orbiting satellite. You have to have a high gain antenna and computers and avionics and things, and you have to have instruments. So we have 2 cameras that you see there. Those are going to take pictures. We have a gamma ray and a neutron spectrometer for elemental abundance, and we have a couple of magnetometers on a boom to determine if there's a magnetic field there. DSOC is actually an extra instrument on board. It's not designed for Psyche. It's a technology demo for deep space optical communication using a laser to transmit information from Earth out into deep space. So you saw the guy there. That's how big the main body of the spacecraft is. And with the solar panels deployed, you see that the Psyche spacecraft is about the size of a tennis court. So this whole project began actually in 2011 when our PI, Dr. Linda Elkins-Tanton, got together with some colleagues at the Jet Propulsion Laboratory in Pasadena and started to discuss the idea of a mission dedicated to exploring an M-class asteroid. And you see they coalesced their ideas to the point where NASA released an announcement of opportunity, or AO, for the next Discovery mission call. The proposal was submitted along with like 25, 28 other ones. And NASA reviewed them and has selected, I think, maybe 4 for development. They get $1 million and basically refine and develop your mission proposal. And then those last 4 are reviewed. And then it was in January of 2017 that we were selected, and along with our sister mission, Lucy. And the idea is that's where you get the funding and that's where you begin the process. So starting in January 2017, we did the development, the design, the preliminary design, the critical design. That was all approved by NASA. And then we built the spacecraft, and that led all the way up till launch. And I'll tell you some more details about that. So here's the spacecraft in the clean room at the Jet Propulsion Laboratory in Pasadena. There's me, and behind that you see one side panel of the spacecraft. You see the big hole with the orange cords there. That's where one of the solar panels would attach. And then behind me and above my head, you see the boom where the gamma ray and neutron spectrometer is. The sticking out, the 2 silver things that you see sticking out the top on this picture on the right are the 2 multispectral imagers. So we shipped the spacecraft. It was finished, shipped to the Cape in 2022, and we were getting ready for launch. However, we had to have a launch delay of a year. And the reason why is the guidance, navigation, and control software that JPL developed was completed, but we didn't have time to fully test it in order to meet that 2022 launch window. So we discussed it with NASA, and they said, all right, take an extra year and make sure it's all tested. And then, when you're ready, we'll launch. And so they did that. It was ready. And obviously, you're not going to launch a spacecraft if you have any question about any part of it there. So they gave us that extra year, and everything tested out. There you see the front side of the Psyche spacecraft with the thermal blankets covering the high gain antenna. And you see the DSOC tube right out there. So that leads us to October of 2023 out at the Kennedy Space Center in Florida. You see Psyche is advertised there, and you see the rocket gantry in the background. I was out there, and we had lots of education outreach that week talking to visitors to the Space Center about our mission. Here's our leadership team from ASU. You see me in the maroon shirt there. To my right on the screen, Professor Jim Bell, who's the lead on the imager, and in the purple, Dr. Linda Elkins-Tanton and her administrative assistant. And then on my left side, or on the other side, two of our administrative staff there. And you see in the background, the Psyche spacecraft mounted on top of a SpaceX Falcon Heavy rocket. Yes, the side boosters are sort of blackened because they were already used 3 times. We live in an era, thanks to SpaceX, of reusable rockets. And so we were the 4th launch of those particular boosters. So that leads us here to the actual takeoff. And I don't know that you're going to hear it. I'll place it here. So applause. I was not taking that video. My wife was. I was looking with my own eyes there and before it disappears in the cloud. And you notice after all this time is when the sound comes. So that's where you hear the rocket thrust there. It takes a while to get there. But here we go. Here's the other video that NASA put out.
David, we're not hearing any of the sound.
Okay, it's not important that you hear it. They're just saying that it launched here. Yeah, I forgot these videos were in here. But basically, it's just showing the launch here and the successful liftoff, booster separation here. Firing up the engine to boost it out of Earth orbit. The boosters coming back and landing at the Kennedy Space Center with the double sonic booms. And then the spacecraft separation. Just saying the Psyche spacecraft going off into deep space there. I actually had to wait until that evening when the imager team got together there at Port Canaveral, and Jim Bell came in and I said, did the solar panels deploy? He said, yeah, they deployed, no problem. Yeah, we got everything's going just fine. So I had to worry about it all day. Anyway, so that was our launch in October of 2023. And you see this graphic here. Because we're using solar electric ion propulsion to move through the solar system, that undergoes a spiraling orbit. We go out into the main belt. We're going to come back and do a Mars gravity assist in May of 2026. Then we're going to go back out and then eventually catch up with asteroid 16 Psyche in August of 2029. So yeah, we do have another 4 years to wait there. The blue dots on these orbital tracks are the time that we're testing the DSOC, the Deep Space Optical Laser communication there. And then once we get to Psyche, you notice the orbits are split up. There's A, B1, D, C, B. See, this is a consequence of the 1-year launch delay. It was supposed to go A, B, C, D. But, we had to split it up because when we get there, the southern hemisphere and the equatorial region of Psyche will be in sunlight, but the northern hemisphere will be in darkness. So our main orbit where the whole thing is lit up, we have to wait until B2 to get at that. So we're going to do our observations a little bit out of order, but we will still be there to cover everything. So I mentioned solar electric ion propulsion. This is something that was tested on earlier NASA missions and worked very well on the Dawn mission to Vesta and Ceres. So it uses Hall thrusters. It basically, you use electricity generated by the solar panels and xenon, a very low mass fuel. You ionize the xenon, you propel it out the back through against a magnetic field, and that causes the propulsion. And its advantage is that because it's a low mass fuel, it reduces the mass and therefore reduces the cost of the spacecraft. The negative is that the acceleration is really low and it's going to take you longer to get where you're going. But in an era where there's constrained budgets available to do all these types of missions, this is a good compromise to take a little bit longer to get there, but then use this sort of advanced technology of solar electric ion propulsion to get to where you want to go. And the main body of the spacecraft was built by Maxar Technologies. They have a long history of Earth orbiting spacecraft using solar ion propulsion. And, they are the ones who, this is their first deep space mission. So this is what it looks like in graphic form. When we get to asteroid 16 Psyche, you see there's basically 4 different types of orbits. Each one is at a different altitude. We're going to get successfully lower in altitude, and each orbit is optimized for a particular type of imaging. First thing we'll do a satellite search on approach to make sure there's no moons around that, because you don't want to go into close orbit if there's a moon. Doubtful if there would be one. We probably would have discovered it by now. Orbit A will do imaging and mapping, get the initial magnetic field and gravity measurements. Orbits B will focus on higher resolution topography and imaging for geologic mapping. Orbit C is the high resolution magnetic field and gravity measurements. And then orbit D is where the gamma ray and neutron spectrometer will get the compositional information. And that's basically what it says right here. We're going to go, when we get into our first orbit, we'll be looking at the surface about 35 meters per pixel. We'll get as good as maybe 4 meters per pixel in the final set of orbits. So what instruments are on the spacecraft? I've sort of mentioned them. The multispectral imagers, 2 of them for redundancy, are led by ASU. Malin Space Science Systems in San Diego built them. So they will have cameras taking pictures of the surface, looking for the morphology or shape of surface features, the albedo or brightness. And there's also 7 color filters that are going to be focused on looking for silicate and sulfide metals that might be associated with metals. And then by looking at the surface at different look angles and different orbits, we'll be able to generate a topographic map, a digital terrain model of the surface. The magnetometers were built, they are led by MIT, and they were built by the Danish Technical University in Copenhagen. And they measure magnetic fields to a sensitivity of 0.1 nanotesla. I don't know how much that is, but it's very, very small, so very precise measurements. If there are parts of Psyche that have a magnetic field where other parts don't, it will be able to detect it. The gamma ray and neutron spectrometer was built by the Applied Physics Lab at Johns Hopkins University in Maryland. Gamma ray spectrometers are designed to measure elemental abundance, the amount of iron and nickel and silicon and potassium and a bunch of other elements. The neutron spectrometer is designed to seek out hydrogen abundance. So if there's water ice there or hydroxyl in hydrated minerals, that instrument will be able to tell us about that. And then finally, we can use the spacecraft itself as a gravity science experiment. Basically, you can measure very precisely the Doppler time delay and the signals coming to and from the spacecraft. When a spacecraft goes a mass con, it pulls it down slightly, region of less mass, it pulls it up. You can measure that very precisely. And from that, we'll be able to develop an interior model. If in case this is an object that's not just a planetary core itself, but if it does have crust and mantle on it. So for those of you who like filters on your telescopes here, these are the filters we have here. And as I said, a broadband clear filter, filters to look for oldamite, which is a sulfide associated with metals, and then also simulations of red, green, blue color, as well as filters to look for silicates like olivine and pyroxene. So this is a mapping mission. So that means we get into orbit, we just paint the surface of the asteroid with images, and you can see the footprints from the different orbits there as we just cover the surface to basically see what it looks like. And this is just showing in graphic form what I just explained about how we get the gravity model of the interior. This is an animation, no sound. It's an idea about these hit and run collisions where you can knock off crust and mantle and you could have left behind the iron nickel core, or maybe it was the impactor that hit the thing that stripped it of its crust and mantle, and maybe the core of that impactor is what's actually left over. We don't know yet what that's going to be, but that's something we're going to look into when we get there. So you've probably seen this artwork by artist Peter Rubin. This was from our initial mission proposal showing a fully metallic asteroid 16 Psyche with craters, maybe some sulfur flows that were expunged from the interior. We have a series of questions or alternatives about what this could be. Was this unmelted metal? Was it something that solidified from the inside out, from the outside in? Or could it be a metallic rubble pile? The way that you figure that out is not through any one piece of information from one instrument. You have to combine it from all of the different instruments, as I'll show you in a moment. These two pieces of artwork, also by Peter Rubin, show more updated versions of what 16 Psyche could be. And this is thanks to all of our planetary astronomer friends who were studying Psyche for those 6 years while our spacecraft was being built. The cartoon or image artwork on the left shows a metallic Psyche, but with a lot more coverage of silicate gunk, either leftover crust or mantle, or maybe stuff deposited by S-type asteroids. The artwork that you see on the right is an asteroid where the silicates and metals are more intimately mixed, perhaps like what you would have on a palisite. So these are also alternatives that could exist for this asteroid. So here's an example of what you would do. You would basically have to develop a decision tree to try and figure out what does the multispectral imager tell us about the way the surface looks. Are there sulfide minerals and silicates over different parts of the surface? What does the gamma ray spectrometer tell us about the nickel content? Is it there? Is it heterogeneous, or is it more specific? What does the magnetometer tell us about the magnetic field? And as you study this in different ways, put these different things together, we're going to be able to come to a list of possibilities of what this asteroid might be, or perhaps eliminate possibilities of what it cannot be based on the data that we receive. Now, as a geologist, I'm very interested in what does geology look like on a world made out of metal. So this is from the Ames vertical gun at NASA Ames Research Center in California, where you had an iron ingot that was impacted by a metallic projectile. And you see the crater that formed where the sort of the ejecta is like frozen on that. That's a hypothesis for what a metal object would look like if a crater formed in it. Or if it's a palisite, how different would it be if you impacted something that was a combination of olivine grains and metal matrix there? That would certainly produce a different type of regolith than anything that we've really seen before. So that's sort of where we're at. We're launched, we're cruising through the solar system. Every 6 months, we do a periodic maintenance and calibration. This one was from July of 2024, and here you see the Wishing Well star cluster right there. I'm sure you guys have seen it with your own telescopes there, but this is a good test to make sure that our imaging cameras are working and to collect data we need to use to develop the calibration pipeline before we get to Psyche. We'll do the same thing when we do our Mars flyby. This is from January's PMC, and this time we've looked at Jupiter. Actually, Jupiter and Mars. You see Jupiter and Mars are in there. And then in the inset there was enough sensitivity that we could actually see the Galilean satellites. So Io, Europa, Ganymede, and Callisto were also visible there, which I thought was pretty cool considering how much work I've done on Jupiter's volcanic moon Io. So that's where we're at with the Psyche mission. Let me just say a couple of things about the other missions. So I've already mentioned OSIRIS-REx that returned the samples from Bennu. And you probably heard the press conferences just about a month and a half ago about them finding the elements related to amino acids, the building blocks of life, as well as hydrated minerals that evidently formed under some form of hydrothermal alteration. So the materials that make up asteroid Bennu, carbonaceous asteroid Bennu, basically came from some sort of a mud ball. Early in the history of the solar system, you still had something with enough heat and with ice to melt it and cause hydrothermal reactions. It's absolutely fascinating. What great results that have come from those analysis of the samples from Bennu. Here you see the spinning rubble pile asteroid Bennu, and here you see some of those materials that were brought back from the sample container. The Lucy mission, we are also involved in that at ASU. My colleagues, Professors Phil Christensen and Jim Bell, are on this Trojan asteroid multi-flyby mission. It's going to be a while before we get to the Trojans, but I think it is on the April 20th. So this coming weekend, about 1:15 in the afternoon, the spacecraft's going to fly by the main belt asteroid Donald Johanson, and we'll get to see what another asteroid looks like. So stay tuned for that, and you'll be able to see what we all be able to see what that looks like. So when you talk about metals, metal asteroids, inevitably the subject of space mining comes up. So many asteroids contain valuable resources that we'll need to help build a spacefaring civilization. And our PI, Lindy Elkins-Tanton, once did a calculation. If you recognize the size of Psyche from Earth-based telescopes and assume a composition typically similar to iron-nickel meteorites, then the calculations suggest that asteroid 16 Psyche could have enough metals valued at 100,000 times the gross national product of all nations on Earth, or $10,000 quadrillion. Now, obviously, that's not quite right, because even if you had all that and you brought it back to Earth, the metals markets would crash. They wouldn't be worth as much. But it's the implication that is really interesting about that is, does it have those kind of resources? So there have been companies like Planetary Resources and others that have been making plans to search near-Earth asteroids to look for various types of resources that we could utilize. Now, it's not going to be as simple as that top graphic where you suck an asteroid in on one side of a space station and now build space station components on the other. It's going to be much more complex than that. It will take decades for humanity to figure out how to mine asteroids to build this kind of infrastructure. And it will be a challenge for humans to work in that kind of microgravity. But the rewards for doing something like that, identifying space resources, whether they be in asteroids, whether they be water ice in shadowed regions of lunar polar craters, or helium-3 and the lunar soil, all of these things are going to be important for building a spacefaring civilization. So that takes me to my concluding slide. So asteroids are the rocky remnants from the formation of the solar system. On January 4th, 2017, NASA selected Arizona State University to lead the Discovery-class robotic mission to M-class asteroid 16 Psyche. Psyche, as a spacecraft, just like the Dawn spacecraft last decade, uses solar electric ion propulsion to move through the solar system. We carry 3 instruments to study the asteroid: visible imagers, magnetometers, and gamma ray and neutron spectrometers. We successfully launched October 13th, 2023. Friday the 13th may have been a bad day for the Knights Templars in 1307, but it was a very good luck day for us back in 2023. We are basically cruising through the solar system right now. We are looking forward to our Mars flyby in May of 2026, we'll be getting ready for that, and then arrival in August of 2029. So what you see here is the rotating telescopic shape model of the asteroid, and you can see potato shape with indentations. The thing that's interesting is the graphic on the bottom. That is a combination visible and radar albedo map of the surface. And the thing that you'll notice is that it isn't all the same. There's brighter areas and darker areas. There's things with different radar albedo. So that is telling us that the asteroid Psyche is heterogeneous. There are different areas on the surface. That means there's geologic differences. There are places that we're going to want to explore. So we will learn something new with that. So I'm going to put it on this slide over here. We just made a new digital poster for what is M-class asteroid Psyche, where I talk about those different objects. And then on the back of this poster is a graphic that explains a lot of the stuff that I talked about. So if you want to get out your phones really quick and scan that QR code, that will go to my lab's website, the page that has all the digital posters, and you can be free to download those posters, and not only for Psyche, but for any of the other missions. There's posters from Juno with the Io observations. There's Mars Express posters of Mars. There's posters from Vesta and Ceres and Pluto, and just a bunch of different ones there. So you can do that. So I think I am going to stop sharing. I will say thank you very much for your attention, and I'm happy to take any questions.
Wow, that's really great, Dave. So we do have quite a number of questions, so let's just kind of get right to them. Fairly early on, we had Subhashri asked a question who said that it reminded him of the Philae lander designed by the European space mission, which was intended to land on a comet, but it landed but didn't communicate. So is there a plan for NASA to do something similar with asteroids and comets?
Yes, matter of fact, the sample return missions, I think it was Hayabusa 2, also carried a German-built a lander that dropped onto the surface, and they actually got data back from that. Unlike the Philae lander, they got, you're right, it didn't land quite right. So the answer is yes, but remember, we have to do things sort of in order in time. So you need to figure out the one sweet spot where you want to send a productive lander, and you need an orbiter mission to do that first. So before we go back to Psyche with a lander, assuming there's anything there that justifies having a landed mission, we need to characterize it globally, and that's what we'll do with this mission. But the short answer is yes. As we discover places that where it's justified to put landers down, we will. The ones that they did for Hayabusa 2 were sort of tech demos, just to see if you could do it. Philae on Comet 67P, yeah, they had hoped that would work, but there was just a challenge. The harpoons that it fired didn't stick into that ice. It's sometimes the surface really surprises you. We found that out with the InSight mission that landed in Mars when the heat flow probe couldn't be pounded into the surface there.
Great. So we had a question of curiosity. So Paul and actually a couple others were wondering, in the image on launch day, why were you all holding up 3 fingers?
Oh, the mascot of Arizona State University is Sparky the Sun Devil. So it's common at athletic events when you're doing a cheer for Arizona State that you hold your fingers up like this. This is supposed to be the devil's pitchfork.
Ah, so not that different than what they do at Texas with the hook 'em horns.
Yeah, something like that.
So what's the advantage of being in partial Earth orbit before your departure from Earth's gravity well, I guess you might say?
I sort of, when you launch deep space vehicles, typically your rocket will get you out of the Earth's gravity well part of the way, and then the rockets will come back and land. That gets you up maybe to an Earth orbit altitude, but you need an extra burst of energy to get it from Earth orbit out of Earth's gravitational field completely to put you in one of those solar system traveling orbits there. So yeah, the SpaceX Falcon Heavy got us into an Earth orbit, and then we needed the extra boost to send us out of it and put us on the trajectory to get out there to the asteroid. And then we use the solar electric ion propulsion to build up the momentum to increase our spacecraft speed to match that of the asteroid with the help of the Mars Gravity Assist.
Okay. So Silvio has a really interesting question. How does NASA control the flight over time of such a mission to not hit any other asteroids or space junk in low or medium Earth orbit? And I guess we have this, we're all fans of science fiction, but all the images you see of, you fly through the asteroid belt and it's dense with all these things. And so what's the reality, and how do you avoid missing stuff?
Yeah, those of us who grew up watching the second Star Wars movie, The Empire Strikes Back, which came out in 1980, where you see the Millennium Falcon and the TIE fighters flying around these asteroids. The asteroid belt is really not like that at all. There is tons of space between the individual rocks. NASA has sent space missions through the main asteroid belt to the outer solar system quite a lot. There were Pioneer 10 and 11, Voyager 1 and 2. There's the Pluto mission, the missions to Saturn. So that would have been Cassini, the Galileo and Juno missions. So those all went through the asteroid belt and not one of them hit anything. It's, as my old astrophysics professors used to say, space is a big place and there's just quite a bit of space out there. So it's very unlikely that a spacecraft will run into something on its way. I guess I better knock on wood because our spacecraft is still in the main belt and it's going to be there for a while. So yeah, that hasn't, at least up till this point, has not been a danger.
Well, Charles asked an interesting question too. I like this one. When Psyche flies past Mars, will it turn on any instruments and do some testing of the instruments or make observations of Mars as it goes by?
Absolutely. Mars is going to be an excellent test to turn on the instruments and see if they're working properly. I mean, you get a certain amount of information by shooting, like pictures of stars and standard stars and clusters and distant images of planets. But to see what a planetary surface would look like, we're definitely going to turn on the imagers and do a bunch of observations as we do our flyby of Mars. I think the gamma ray and neutron spectrometer and the magnetometer, I think they're on all the time anyway. They're on during the cruise just to monitor solar storms and things like that. But yes, we will be turning them on. We will get that calibration data so that we're in great shape when we get to asteroid 16 Psyche.
And kind of sticking with this idea of the flight. So Christopher asked, with the ion propulsion, how do you slow a spacecraft down when you reach your target? Is it manipulating the gravitation all around, to match its trajectory with that of the asteroid?
Yeah, we know the orbits of objects in the solar system very, very precisely for the ones that have been discovered. The ephemerae or ephemeris for these things is really well known. So it's very easy, well, not easy, but if you know what you're doing, to figure out exactly what you need to do to get a spacecraft to any of these objects there. So the solar electric ion propulsion is slowly building up a velocity and momentum so that when it gets there, we'll basically be in orbit, and then 16 Psyche will sort of capture us around. And, we'll just be able to use our cold gas thrusters and reaction wheels to orient things. We'll be using the ion propulsion to drop us down as we go from orbit A to B1, then B1 to D, then to C, then back to B1. So we use that to do that. But yeah, you can figure that out very precisely. And it's really a wonderful new tool in our toolbox for studying these low gravity bodies.
So kind of thinking about the gravity, and so we had a question, every once in a while we have a really good one from YouTube, and so we have a question: do any asteroids known to have any thin atmospheres or magnetic fields, and are there gravitational forces of any significance for a spacecraft passing by or to overcome in taking off from an asteroid if you were to land on one or leave it to go someplace else?
Yes. Anything that has mass has gravity. And, obviously, the bigger it is, the more mass it has, the more gravity it has. For these small bodies, they do still have gravity, and when we get into orbit, we will be in orbit unless we use the propulsion to leave and go somewhere else. But it is there. It's something you have to deal with. Now, as to your question, I don't think we've detected magnetic fields on other asteroids yet, but we may not have had the right instruments to do that. We have specifically had magnetometers on Psyche. There was supposed to be magnetometers on Dawn, but due to cost overruns, they had to take a couple of instruments off the Dawn mission. And I think now we sorely missed having those on there. We wish we would have been able to have them. So hopefully that answers the question.
So Christopher asked a question, how common are metallic asteroids compared to other types? Is there really enough metal in them to justify mining them, as some suggest, or do we not know and that's why we're going?
We don't know, and that's why we're going. Yeah, this is the first mission to an M class, a metallic asteroid. We've been to stony type, S types, and we've been to C types. But we haven't really seen a large M type up close. Now, actually, I think 21 Lutetia was classified as an M type, but we didn't get a lot of good data from that. I mean, you just look at it; it just looks like a regular asteroid. So yeah, we're basically going to look at it, and we need to characterize it from orbit, what it's made out of, and are there sufficiently abundant metallic deposits there, and are they in a state that would be accessible to mining? So it's not just what's there, but what condition it is in. But this is pure exploration. This is seeing something that we've never seen before. And if it's like every other NASA planet or planetary object that NASA has explored, there's going to be something there that surprises us, something that we didn't expect. And that's part of the thrill of exploration of the solar system.
So the other part of that question, and I think you may have alluded to it in the presentation, was what's the approximately present percentage of asteroids that are considered metallic, they're chondraceous and stony? What's the approximate percentages?
Yeah, I don't have that number in my head. I know that the largest percentage of asteroids, I think, are the C type, the carbonaceous type, with stony type second. But there's not an excessive number of M types. I can only think of Calliope and Cleopatra, and maybe one other whose name I don't remember. But there's those four. I know there's more than that, but they're not a huge number of the different types of asteroids that are out there.
Okay. So when we're kind of characterizing this, and this was in one of the slides, you had what appeared to be almost a dichotomous key, or a thing where you go and you make two choices and try to determine, what the characteristics are. And so, and I think it was on this slide that you alluded to a link between nickel and gamma rays. Could you, elaborate on that? What's the connection between them?
Well, a gamma ray spectrometer is a type of remote sensing instrument that's designed to detect elemental abundance in the upper surface of any planetary object. We've been flying gamma ray spectrometers, I think, going back all the way to Apollo. But they are optimized, and nuclear spectroscopy is optimized for determining these particular types of elements. And the one on the Psyche spacecraft is in particular developed to be very highly sensitive to nickel, not just iron, but nickel, because iron and nickel are major components of planetary cores. So it's just, the thing with gamma ray spectroscopy is there's an awful lot of modeling to interpret the data compared to, say, like looking at an image. An image is sort of like a photograph. And, depending on how well, how much light is returned, you can look and you can say, oh, well, that's an impact crater. That is a scarp. That is a mountain, or that is a volcano or a lava flow. Those are really easy to do. Whereas it takes a lot more effort to get the data out of nuclear spectroscopy. So, nickel is just one of many elements that's going to be able to be detected by that instrument there. And they will have to do their fair amount of work to make sure they get the statement that, okay, well, Psyche is made out of this percent of nickel. Or maybe this part of the surface is that much nickel, but that part is different, which would mean that heterogeneity is there for some reason.
So, and just to clarify about the gamma ray spectrometer, it's not that the materials are actively giving off gamma rays, that the spectrometer is actually going to zap, you might say, the asteroid and the materials with it. Then you're going to look at the reflection of that and as it comes back off. Is that correct?
Well, actually, the way a gamma ray spectrometer works is studies gamma rays that are released when cosmic rays interact. They strike a planetary surface, and then the interaction of those cosmic rays, galactic cosmic rays, shoots off the gamma rays. And then the energy of those gamma rays is very specific to each of the different types of elements, and this spectrometer measures that. So it's not an active remote sensing instrument like a radar is. It's like a visible light camera. It's looking at the stuff coming off the surface and making measurements based on that. That's what we would call a passive remote sensing instrument.
Okay. Because I know that, if you do things like X-ray fluorescence or something here on Earth, you're zapping things actively with things. So that, that's important. I just kind of assumed that you were zapping with some gamma rays, and I didn't realize that it was from that they were generated by cosmic rays that were hitting the asteroid. So that's interesting.
Yeah. The only thing that we're zapping is the Deep Space Optical Communication Test Instrument. We've been going back and forth. Signals are basically sent from Mount Palomar in California, and the spacecraft receives the laser and the information. And then the Psyche spacecraft has been using its transmitter to send it back to Mount Palomar. And I think there's a famous video from last year, video that was transmitted from the spacecraft back to Earth. It was a video of somebody's cat playing around.
So we are almost out of time, and so I'll do one more question here, and I apologize to all the questions that we weren't able to get to here. But one of the questions that kind of comes up is that, as you get there, and what do you anticipate, what kind of surprises do you think are in store for us? I mean, you kind of have this idea of what you're looking for, but are you anticipating any surprises when you get there?
Anticipate, yeah. Well, we can make educated guesses, and there's been an awful lot of research that's been going on by our PhD students and postdocs looking at possibilities of what we might find there. For example, could this asteroid have a regolith? We've seen regolith or soil fragmental materials on all of the other asteroids of some form. I mean, some of them have very fine-grained stuff like Eros or maybe some of the others. But then you have Bennu and Ryugu, which are rubble piles, which are much larger fragments there. What would a regolith be on something that has a major proportion being metallic? What would a metallic regolith look like? So we've had a whole PhD student studying that. I'm not going to get my hopes up for lava flows or volcanic features because I did that for Vesta. And when we got there, that asteroid was so heavily pulverized, there really wasn't any, thing preserved. Just one laccolith-like dome on the surface, rich in diagonite material that was exposed by an impact crater. That was really the only igneous-related feature on the surface of asteroid Vesta. So I'm not expecting there to be lava flows, but there could be elemental signatures of what they call iron volcanism, where molten iron actually erupts out onto the surface and sort of like an iron or a metal lava flow, or maybe something rich in sulfur that was part of that original sulfur they thought would have been expunged onto the surface there when the core crystallized. So I would love for there to be something like that. That's just really hard to know at this point. So yeah, I fully expect there to be surprises. And it's going to be really, really fun when we see what those surprises are.
Yeah. Well, I'm looking forward to, finding out what we get. There's been such an emphasis on asteroids over the last number of years and the missions. And, it's just, fascinating. We kind of discount asteroids, but it turns out that we can learn so much about the origins of the solar system and why things are the way they are by studying these little things that we sometimes forget about.
Yeah, I think the reason why that is the case is because there was just so much focus. First it was on the moon during the Apollo program, and we started sending robotic probes. We did Venus, we did Mars, we did Mercury, and we did the Pioneers and Voyagers to the gas giant outer planets, and then started looking at their moons. And then we just hadn't gotten around to asteroids. And finally, we late 90s and started with 2000 with the Near Earth Asteroid Rendezvous mission. Now we finally started to get asteroids, and we've done, like I said, we've done S-type with Eros, we've done C-type. Ceres, dwarf planet Ceres is actually a C-type. We did V-type with Vesta. Lucy is doing dark and primitive D and P types, and Psyche is doing M types. So there's not that many places of terra incognita left in the solar system, but we are finally starting to hit that with these missions to these various types of asteroids.
Let's see. Kat, if you could mention about that, it looks like I need to change the permissions on this thing.
Interesting, because I click on it and it looks normal for me.
Yeah, I see a comment in the chat about what are all these brilliant scientists going to do when the government keeps denying funding? Yeah. Well, elections have consequences. Yeah, there are concerns about what's going to happen with the budgets of NASA and the Science Mission Directorate. I would just direct you to the Planetary Society, maybe, and not as an ASU professor, but just as another citizen of the United States in science. And if you're really passionate about, space science, there's things that you can do about that. So take a look at the Planetary Society website, and they'll tell you some options.
I think I've got the survey fixed now. So somebody give it a try and see if it works.
Recording has stopped.
Yeah. Well, while we're still fiddling with that, please join us for Cosmic Conversations on Wednesday, April 23rd. That's next week. And so hopefully we'll have some more information about this and a chance to chat about what we're learning here this evening. And Jeff indicates that it works, and John did too. So thank you very much. And so here's the registration link for Cosmic Conversations for next week. And our next webinar is Thursday, May 15th, when we welcome Dr. Eric Mamajek, who will discuss the search for exo-Earths using NASA's Habitable Worlds Observatory. And so we also want to thank you, David, for joining us again. You know, it's always a delight to have you. I think this is the second time now, and I hope to have you back here in a couple more years when we know a little bit more, and hopefully we'll all still be around when it goes into orbit there at Psyche.
Hopefully so, yes. Fingers crossed on that. Pleasure to be here with the Night Sky Network. You guys, I wish you dark skies and great observing until I am able to talk to you again sometime.
All right. Well, thank you so much.
Thank you all.
Take care, everyone. Good night.
Good night.
Good night.
I'm gonna go ahead and end the stream now.
And
There's always a delay.
yeah. And Kat, you've got the button.
All right. Good night, everybody.